Imagine watching a star just disappear. No explosion, no fireworks, just gone. That's exactly what NASA witnessed, and it changes everything we thought we knew about how black holes are born. Welcome back. Today we're talking about one of the most jaw-dropping discoveries in recent astronomy. NASA's telescope actually recorded, in real time, a massive star silently collapsing into a black hole. Not with a bang, not with a supernova explosion that lights up the galaxy, just a quiet, eerie fade-out, like a candle being snuffed out in a dark room. And the more you understand what actually happened, the more unsettling it becomes. Let's start from the beginning. 2.5 million light-years away from Earth sits the Andromeda galaxy, our closest galactic neighbor. Inside it, there was a massive star. Scientists called it M31 2014 DS1. Not the catchiest name, but what this star did absolutely earns it a place in history. Now, normally when a massive star reaches the end of its life, it goes out like a rock star. The core runs out of fuel, gravity crushes inward, and then, boom! A shockwave blasts the outer layers apart in a supernova explosion so bright it can outshine an entire galaxy for weeks. It's one of the most violent events in the known universe. But M31 2014 DS1 didn't do that. In 2014, astronomers noticed something odd. The star suddenly brightened, but only in infrared light, not visible light. Infrared. That's the kind of light our eyes can't see. The kind that tells you something is heating up beneath the surface. Something was happening deep inside this star. Then, slowly, the star began to dim, and dim some more. By 2023, 9 years later, it had faded in visible light by a factor of more than 10,000. That's not a star dimming, that's a star vanishing. Scientists went back through archival data from NASA's NEOISE mission, that stands for Near-Earth Object Wide Field Infrared Survey Explorer, along with data from other ground and space telescopes going all the way back to 2005. They pieced together the full timeline of this star's death, and what they found was extraordinary. The infrared brightening in 2014, that was the star shedding its outermost layers. The core had run out of fuel. It tried to explode. It produced a shockwave, but the shockwave was too weak. It couldn't push the stellar material outward with enough force. So instead of blasting apart, most of the star's mass just fell inward, collapsed under its own gravity, and in doing so, it created a black hole. No explosion, no dramatic farewell, just silence, and then darkness. Scientists call this a failed supernova, and it is exactly as strange as it sounds. Now let's talk about what was actually born in that darkness. Because black holes are one of those things where the more you learn, the less you feel like you truly understand them. A black hole is not actually a hole. That's the first misconception to clear up. It's a concentration of matter, sometimes an almost unimaginable amount of matter, packed into an incredibly tiny space. The star that collapsed into M31 2014 DS1's black hole was massive, and all of that mass, compressed beyond a certain point, creates a gravitational field so intense that nothing can escape it. Not gas, not dust, not light itself. The boundary of a black hole is called the event horizon. Think of it as the point of no return. Cross that line, and you are not coming back, because even if you were traveling at the speed of light, gravity would still pull you inward faster than you could escape. The event horizon isn't a physical surface you could touch. It's more like an invisible threshold, a boundary written into the geometry of space itself. And inside, we genuinely don't know. Physics as we currently understand it breaks down at the center of a black hole. The math produces what scientists call a singularity, a point of infinite density, which is really science's way of saying our equations stop working here. What actually exists at the center of a black hole is one of the deepest unsolved questions in all of physics. Now here's a question that might seem obvious, but is actually fascinating. If black holes don't emit light, how do we find them? Because they're invisible. Completely, totally invisible. You cannot point a telescope at a black hole and see it directly. So how do we know they exist at all? The answer is, we watch what they do to everything around them. When a black hole is surrounded by gas and dust, which happens often, since space is full of the stuff, that material gets pulled toward the black hole and forms what's called an accretion disk. Picture water spiraling down a drain, except the drain is an object with the mass of millions or billions of suns, and the water is superheated plasma moving at a significant fraction of the speed of light. That accretion disk glows intensely, emitting X-rays and other radiation that our telescopes can detect. That's actually how the infrared brightening of M31 2014 DS1 was spotted in the first place. The dying star was shedding material that heated up and glowed in infrared before the collapse. Another way we find black holes is through the motion of stars. If you see stars orbiting around an empty-looking point in space, moving in tight, fast, precise ellipses around nothing visible. Something massive is there. This is exactly how scientists confirmed that our own Milky Way galaxy has a supermassive black hole at its center, called Sagittarius, a star. Tracking the orbits of stars near the galactic center over decades revealed an invisible object with the mass of about 4 million suns sitting right in the middle. That discovery won the Nobel Prize in Physics in 2020. There's also gravitational waves. When two massive objects, like black holes, spiral toward each other and merge, they send ripples through the fabric of space-time itself. These ripples travel at the speed of light and can be detected here on Earth by incredibly sensitive instruments. When the LIGO detectors first caught these gravitational waves in 2015, it was the first direct confirmation of something Einstein had predicted a century earlier. And there's gravitational lensing, the way a black hole's gravity bends light from objects behind it, distorting and magnifying their appearance. Scientists can use this effect to detect black holes that would otherwise be completely invisible. Before we go further, let's clear up two myths that seem to stick around no matter how many times scientists address them. Myth 1. Black holes are wormholes. They are not. A black hole is not a tunnel, not a portal, not a shortcut through space. There is no other side. Whatever falls in is gone. The idea of wormholes is theoretically interesting and scientists do explore it mathematically, but a black hole itself is not one. Myth 2. Black holes suck things in like cosmic vacuum cleaners. This one is almost perfectly wrong. Black holes don't pull matter in from a distance any more than any other object of the same mass would. If you replaced our sun with a black hole of identical mass, which would be a very small black hole, by astronomical standards, the Earth would continue orbiting it exactly as it does now. Nothing would be sucked in. The planets would just get very cold and dark. Black holes only become dangerous to nearby matter when that matter gets close enough for the extreme gravity at short range to take hold. Back to M31 2014 DS1. What makes this discovery so significant, beyond being extraordinary on its own, is what it tells us about how common this might be. We've always known that massive stars die. We've always assumed most of them go supernova. But if some fraction of them, maybe a significant fraction, quietly collapse into black holes without exploding, that changes our accounting of both supernovae and black holes in the universe. The research team has already identified another candidate, another massive star that may have undergone the same silent collapse. If this is a pattern, if failed supernovae turn out to be a regular mechanism for black hole formation, it means there could be many more black holes out there than we've estimated, born not in spectacular explosions, but in quiet moments of surrender to gravity. There's something almost philosophical about that. The most extreme objects in the universe, entities so dense that they warp space and time, so powerful that light itself cannot escape, being born not with a bang, but with a whisper. And all of this was uncovered not by some new cutting-edge telescope, but by going back through old data, archival data, records that had been sitting in storage since 2005. The discovery of a star becoming a black hole was hiding in data we already had. Scientists just needed to know what to look for and how to piece it together. That's actually one of the most exciting aspects of modern astronomy. We have accumulated so much data from so many telescopes over so many years that entirely new discoveries are waiting inside archives, waiting for someone to ask the right question. NASA's NEOISE mission was designed to track near-Earth objects, asteroids and comets, that might pose a risk to our planet. But its infrared data turned out to be the key piece of evidence that revealed a star dying to 0.5 million light-years away. Science does that. Tools built for one purpose illuminate something completely unexpected. We are living in a remarkable era of astronomy. We have imaged a black hole directly. The famous photograph of the black hole at the center of galaxy M87, released in 2019. We are detecting gravitational waves from black hole mergers across the universe. We are watching stars orbit the black hole at the center of our own galaxy in real time. And now we have watched, through painstaking reconstruction of archival data, an actual star collapse silently into a black hole in a neighboring galaxy. Each of these is a window into a universe that operates by rules almost incomprehensibly different from our everyday experience. Places where time slows down, where space curves, where matter is compressed beyond any physical state we can recreate on Earth. Black holes are not the end of the story. They are in many ways the beginning of the deepest questions we have about the nature of reality itself. What happens inside an event horizon? What does matter look like under that kind of compression? Is information truly lost when something falls in, or does it escape somehow, encoded in radiation, in gravitational waves, in something we haven't yet imagined? These questions are being actively worked on by some of the sharpest minds in physics, and discoveries like the silent death of M31 2014 DS1 remind us that the universe is still full of surprises, still capable of doing something we didn't expect, even after decades of watching. A star 2.5 million light-years away ran out of fuel. It tried to go out with a bang and couldn't, so it simply folded inward, quietly, completely, leaving behind a shroud of hot gas and dust, and something new, something dark, something that bends space itself. That's how a black hole is born in silence. And NASA was watching.